Thank you, Dr. Ursa, for the kind introduction, and thank you, Dean Georgiopoulos, for the invitation and for this great opportunity. Greetings to everyone. I'm Veeraraghava Raju Hasti, go by Raju, an assistant professor in the School of Modeling, Simulation and Training. My talk today is going to focus on modeling and simulations for sustainable energy, developing scientific machine learning methods to realize the adaptive digital twins for real-time simulations of energy systems. I received my MS and Ph.D. from Purdue University, West Lafayette, Indiana, and then I worked as a research assistant professor at Purdue and then at North Carolina State University before joining here at UCF. My interdisciplinary research is focused on developing digital tools like adaptive digital twins for real-time simulations of complex physical systems, leveraging state-of-the-art advances in several disciplines as shown here, like artificial intelligence, scientific machine learning methods, digital twins and immersive simulations, energy systems modeling and optimization, and so on. Regarding my teaching, I will be teaching here in the spring 25 mathematical foundations of modeling and simulations, and a new course in fall 25, that is AI for sustainable energy. I integrate research into teaching methods to provide experiential learning for my students. I have listed here a few selected accomplishments from my career so far. So during my tenure at Honeywell, simulation tools developed led to the co-invention of low-emission combustion technology for Honeywell Auxiliary Power Unit, and it is currently used in Airbus A220 aircraft and many other aircraft in the world. So today, I will discuss our research in digital transformation for decarbonization and sustainability, organized into three main thrust areas. Thrust 1, we develop physics-based high-fidelity simulations to understand and deep dive into the physics, and also that helps us to create more training data sets. So this thrust area, we have few projects that rely on traditional physics-based simulations. For instance, we are developing simulation methods for rocket engine instabilities at high pressures, characterization of sustainable aviation fuels, also hydrogen and ammonia fuels for both power generation and propulsion. In Thrust 2, we focus on developing scientific machine learning methods, and this thrust mainly focuses on the use of physics-informed neural network and other physics-embedded neural networks with multimodal learning to develop more generalizable and data-efficient scientific foundation models for real-time simulations. And in Thrust 3, we focus on data-driven systems. So this thrust focuses on purely data-driven AI approaches, such as we have a currently ongoing project on combining the large language models with generative AI and multimodal learning for developing a chatbot for gas turbines and other industrial applications. As you all know, in real world, experimental and operational data is very limited, and sometimes it cannot be shared with academic researchers. So we integrate results from the physics-based simulations and limited operational data with machine learning for real-time simulations. One such example is our techno-economic model for calculating the cost of cycling operations of the power plant, where output from the physics-based simulations and plant data are combined to train a neural network for cost prediction in the real time for the plant managers and operators. So we are also working on predicting the flashback and early detecting in hydrogen-fueled gas turbines to enhance the power plant safety using simulations. In these cases, the governing physical laws were not embedded directly into the neural networks. So this I will discuss later. Today, I will focus more on the power plant cycling model that I just discussed, and provide also show you an AI software that we developed for real-time usage on the at the plants. I will also briefly discuss sustainable aviation fuels characterization, followed by a deeper look into the scientific machine learning using physics-informed neural networks that integrate governing physics equations with limited data to enable adaptive digital twins for real-time simulations. As you all know, the evolving energy landscape looks very complex with several sources to address decarbonization goals. Today, 60% of the power comes from the fossil fuels, but these plants are incurring financial losses due to the cycling operations subjected to the intermittent renewable sources like solar and wind, as you see in the plot at the middle. So this cycling operation introduces significant challenges for traditional coal and as well as natural gas power plants, like it increases the wear, higher maintenance cost, and reduced efficiency. So as part of the DOE sponsored project, our work addresses these issues by developing adaptive data-driven approaches to optimize the cost and performance of cycling operations. So we developed a physics-based model first that computes the energy efficiency, exergy destruction, and accounted for various operational and maintenance costs during the cycling events, integrating all the plant operational parameters. By combining this simulation data with 21 years of plant data from the Coal Creek station that is located in North Dakota, we created a techno-economic AI model for real-time use by the plant manager and operators to optimize the cost and efficiency and as well as the ramp down and ramp up operations of the plant. This work done in collaboration with National Rural Electric Cooperative Association in Washington, D.C. and Purdue University in West Lafayette, Great River Energy in Minnesota, and Pacific Northwest National Laboratory in Washington. So in this project, we focused only on the steam generation system operations. So here is the user-friendly AI software for plant engineers and managers. So we have deployed this software and they have evaluated at the Coal Creek station located in North Dakota. So this is the first time that quantified the cycling operations of large power plants, but still there are several challenges. I felt like this is a great opportunity for me learning, but it opened up a lot of challenges to pursue and continue in this direction and expand this methodology to other power plants. So what those challenges are, how do you account for the plant-to-plant variations in design, operations, and maintenance philosophies? How do you forecast cycling patterns based on the market-driven energy demand and as well as regular and extreme weather events like cyclones and other cold events? Going forward, we would like to address these challenges and extend the model to the entire plant level operations, and in the long term, extend the methodology to model the grid level operations involving multiple generation plants, consumers, and also regular and extreme weather events forecasting models. Moving on to the other project, I mentioned about sustainable fuels characterization and technology innovation. Here is it summarized. If you look at the evolution of the aircraft, we like to fly much faster and also heavier. So we need more thrust. This is possible with a fuel that has similar characteristics as that of the conventional jet fuel. Worldwide, there are several initiatives to develop a biojet fuel as a drop-in fuel you see in the pie chart. But any fuel that is newly developed has to go through the rigorous qualification process, which takes around 5 years and costs around $4 million US. This is a major bottleneck in the development of any new fuel. So how do we accelerate innovation in the new fuel development? So National Jet Fuel Combustion Program, initiated by the Federal Aviation Administration, National Aeronautics and Space Administration, and Department of Defense, aimed at developing simulation tools. As part of this project, we have successfully simulated and established the first of its kind methodology to compute the engine operability sensitivity to the given fuel characteristics. So one such characteristics is the flame blowout that was successfully predicted in these simulations, and this defines the engine operability. For example, if there is an engine blowout in the real flight, what happens? There is a video on the extreme right in the middle. As you see here, if there is an engine blowout, it leads to a catastrophic failure. So we have developed an AI model for flame health monitoring or engine health monitoring from the exhaust, and also early detection of the lean blowout to ensure the flight safety. So we have used the convolutional autoencoder approach and leveraged the simulations data. Okay, moving on to the next slide about the adaptive digital twins. As I have summarized in my previous slides, physics-based simulations are very time consuming. Sometimes high fidelity simulations takes days. We cannot use such methods for real-time digital twin simulations, and pure data-driven suffers from generalization, scalability, explainability, trustworthiness. So, but we have a strong need for adaptive digital twins for real-time utilization. So by combining scientific machine learning with multimodal learning and on-the-fly learning, we can create dynamic digital twins that simulate complex systems in real time. So these digital twins leverage real-time operational data, historical data, simulations data, and from theoretical and analytical models, and then data assimilation, also from different format of the data. And then it allows for continuous updates and precise decision making. So this also inclusion of the AR, VR technologies and human computer interaction will enhance immersive simulations enabling virtual testing and simulation-driven optimization to accelerate technology innovation across various applications and industries. So let us understand how to create such a scientific machine learning models using physics-informed neural network, because this is the main key element to drive these adaptive digital twins. So, so here is a slide that I summarized physics-informed neural network. So physics-informed neural network integrate governing physics equations directly into the learning process, allowing for more accurate and efficient predictions with limited data. So let's see two simple use cases to get the feel of how these pins work. So I have here listed. The first one is one-dimensional transient heat conduction, where pins solve the heat equation, which is embedded into the loss function of the neural networks. And after training, it predicts the temperature distribution over time beyond the training data set. But if you look at the pure data-driven models, they fail beyond the training data range, say 0.5 seconds. But pins continue to work accurately beyond that limit by leveraging these physical laws. The second is a little more complicated, but this is also yet simple exercise to get the feel of that pins. So two-dimensional Ising benchmark problem, a reference test case for simulating a single bubble rising in a liquid. While traditional physics-based simulations took 211 seconds to solve the trained, but the trained scientific machine learning model using pins completed the task in just 0.45 seconds. But still there is a scope for further optimization. So this demonstrates the significant computational efficiency. So these examples show how scientific machine learning methods with their generalization, data efficiency, and scalability are ideal for realizing adaptive digital twins for real-time simulations. So the scientific machine learning framework leverages a variety of inputs from systems knowledge, mathematical tools, and computational architectures to create scalable, composable, and efficient solutions for complex system simulation. So scientific machine learning is not only computationally efficient and data efficient, but also safe, trustworthy, and adaptive, because these are physics constrained, making it the cornerstone of future real-time simulations of energy systems and beyond. Now, coming to the collaborations, I'm actively seeking collaboration opportunities, building on our strong partnerships within UCF centers and institutes, and also with industries, educational programs, and also involving communities in decarbonization, because this is such a very complex goal to achieve, and also advance sustainable energy systems. So finally, I would like to extend my sincere thanks to all our collaborators and sponsors, including government agencies, research institutions, and industry partners for their invaluable support in making this research possible. Thank you all, and I'm happy to take questions if any.